Today we are going to put the fun back in functions, and we're going to be looking at properties of functions, determining domain and range of functions, determining if a relation is a function or not. It is going to be fun functions the whole time. So before we get started, we need to define what a function actually is. A function is a relation in which each element of the domain is paired with exactly one element of the range. And so what that means is each input goes to one output. The thing I usually think of is a vending machine. If I go up to a vending machine and I press a button, so if I press A1, if there is only one snack option on A1, like Milky Way bars, that is a functioning vending machine. But if I press A1 and I could get either Milky Way or fat-free cookies and I don't know which it's going to be, that is not a functioning vending machine. Because if I want a Milky Way, I definitely don't want fat-free cookies. The birthday relation is if you're listing out different people's birthdays. So I'm going to use my kids' birthdays. So Riley goes to June 28th. Laura goes to March 7th. So right now, does this look like it's a function? Yes, each input is going to only one output. Here, I'll even put mine. Mrs. Mahesky goes to October 31st. Real true story. And then I'm going to actually include, so we still look like we're a function. Now I'm going to include one more. I'm going to include my dad. I'm putting Mr. Klein because he has a different last name than me. That's my dad, and his birthday is also October 31st. True story. I'm not making this stuff up. So, my question, is this still a function? Yes, it is still a function because each of these inputs is only going to one output. People can have the same birthday, so we can have the same output. Or back to my vending machine example, I can have multiple spots where I could get a Milky Way, and that's okay. It's still a functioning vending machine. So we want to look at these four. So go ahead, take a moment. There are four right there on the screen, and they're also in your notes packet. And I want you to circle the ones that you think are functions. And remember, a function is for each input, it only goes to one output. I can go to the same output, okay? But I can't have something going to more than one thing. Just like I couldn't have one person going to two different birthdays. That was not. All right. So now you took a look at those. Do we decide which are functions? So A is a function because A goes to D, B goes to E, and C goes to E. Now, it's okay that B and C both go to E. That is still a function. B is not a function because right here, this value, see how A is going to two different things? Okay, that means this is not a function. However, we could call this still a relation. So there's still a relation, but it's not a function. All right, let's take a look at the next one. A goes to R, C goes to Q, D goes to S. And we have this random B and Q, but that's fine. It's still a function. Each of my inputs is only going to one output. And this one is not a function. And it's not a function. Again, A, that troublemaker. And actually, B is a troublemaker too. Do you see that? Okay. The fact that C and D both go to Q, that's okay. But B can't go to P and R. That makes it not a function. So this one's not a function either. But we can call it a relation. This is a relation, whereas this one is a function. Okay. So the graph represents the amount of money paid at a local parking garage. So basically, This is like I went to the mall, I had to pay to park there, and based on how long I parked, I have different amounts of money that I had to pay. So if I'm only parked for 30 minutes, that would be less than an hour. That would bring me right here, and it'd be $4. So what I'm doing here is along the x-axis, I have how long, and along the y-axis, I have how much. So if I'm using this graph at 2 hours, now I have these open and closed circles. These open circles are not included with this spot. So this first one's a little tricky. It says 2 hours. So when I'm looking at 2, I'm going to do this in green. Looking at 2, and I head up. You can see one has an open circle at 8. That's not the one we want. We want this closed circle that's happening at 12. So if I park for exactly 2 hours, they're going to charge me $12. Oh, but if I didn't park for an hour and 59 minutes, it would have only been 8. Man, I wish I walked faster to my car. All right, 3 hours and 10 minutes. Well, 3 hours and 10 minutes is going to be a little smidge past 3. And that will be $16. Okay, this apparently had 2 questions that are chilling really close to each other. So we're going to move 10 hours over here. All right, so 4.5 hours is right there. $20. Yikes. Where are we? New York City? And then $10 is up here at 24. This must have been a place where it had a max cost, that the highest would be 24. You can see how 24 is hitting that for a bunch of different spots. All right. So this is some vocab that we remember probably, but just in case you forgot, domain is the set of the inputs, okay, which goes along this way. Wow. All right. I could write inputs there. I meant to write domain. We'll put inputs underneath. And then range is the set of the outputs. That probably sounds familiar. Okay. So if we were to go back to this one, the domain here were the inputs, and that was hours from 0 to 24. You could go with interval notation like that, or you could write 0 is less than x is less than 24. Okay, in equality notation or interval notation, depends on what you're more comfortable with. The range is a little spicier here on this one. Okay, so my range is really just 4, 8, 12, 16, 20, 24. So the range, I'm just going to write out those numbers with fancy curly brackets. So excited. 4, 8, 12, 16, 20, and 24. And the reason I don't want to put from 4 to 24 is I don't have 5 as an output. I don't have 6 as an output. I don't have 7 as an output. I don't have 10 as an output. So I want to make sure on this range I just list just the values we have. That one's a little spicy. All right. So the vertical line test. If no vertical line intersects a given graph in more than one place, then the graph is a function. Because again, that's our main idea today. We're putting the fun back in functions. All right, so we want to know, are these functions? Ooh, yes, this one is a function. It passes the vertical line test. The equation for this one is x squared y is equal to 4x minus y. Now, I wouldn't expect you to know that equation from looking at it. Let's see if we can solve it for y equals. Okay, I know it's a function right now. Can solve it for y equals. See how I move the other y over? Now, because I have a y here and a y here, I can pull it out. And I can get y equals 4x over x squared plus 1. So that's the function, okay? And since it's a function, I can also write it as f of x equals. Okay? In terms of this, we could also say a domain and a range. Okay. our domain on this one is all real numbers. So you can see it keeps on going. I don't have arrows written on the end, but it hits the very edge of the graph. So that keeps on going. It's a negative infinity to infinity. Could also write this fancy all real number symbol. And then our range. Well, the smallest we are is this -2. The largest we reach is +2. So it's from that to that. Yes, and we can tell it's a function by looking at the vertical line test. It's a lot harder looking at this equation to tell if it's a function, but we'll be practicing that also. Here's another one. Look at that. Take a look at the picture. Do we think that that one is going to be a function? No, no way. That is not a function because we're not passing the vertical line test. The equation on that one is y squared is equal to 4x squared minus 1. Now, how I can tell that this is not a function by its equation is this y squared. That is going to tell me that we do not have a function. And what happens is, when I take something that's y squared and I try to solve it algebraically for y, I'd have to square root, and I'd have to put a plus or minus in front of that square root because I took a square root, and that's what you have to do. And that plus or minus, you can see you have an input going to the positive answer and an input going to the negative answer. What that will create in the mapping, for example, some number like 1 is going to go to the square root of 3, but it's also going to go to the negative square root of 3. And there's that one input going to two different outputs. And you can see that visually as well. Okay. We can still have a domain and a range. It's a little hard to tell right on this one. Our domain from negative infinity. I'm going to say that's negative 1/2. I know it is, but you would probably be estimating it. And then 1/2 to infinity. Okay. Again, I don't want to include any of this spot in the middle, so that's why I have to have that break. And my range is all real numbers or negative infinity. All right. How about this one? Is this one a function? So what I want you to do is pause the video, and I want you to answer this question at the top of this page. Is the relationship a function? And then I want you to do this one and this one. So all three of these problems, remember them 1, 2, 3. I want you to try them independently. Okay? So go ahead. All right. Well, we'll take a look at those together on Thursday. I'm going to upload those onto Schoology. All right. Let's take a look at this one together. So, function or not? This one is a function. Our domain is from -2 to 5. But notice at the endpoints here, I have these open circles. So I want to use the parentheses on those, or I can say -2 is less than x is less than 5. Either one of those notations. Now I want to do the range. My range is looking, the smallest is here, the highest is here. So we're talking about from here to here. Okay, and we want 1 not to be included, but 4 to be included. So this is saying 1 is less than y is less than or equal to 4. Notice I'm using y for the range because it's the y values. Okay. So how do we determine the domain from an equation? This is a really good question. Okay. So, and I've got a bunch of examples down. So when we're talking about domain, so domain is a really tricky thing. I'm going to kind of put them all together. All right, so if I have a mapping, the mapping looks like this, and that's with the arrows like that we started with. When we have a mapping, we're going to use set notation. We're going to list the values. And we list them in these curly Q brackets. They kind of look like Mr. Incredible's uh, profile. Really big forehead, tiny nose, big chin. Okay? The reason we list the values is we don't know that the values in between them are defined. Same kind of thing is going to happen on a table. So if I have like an input-output table with like X and Y, and boom, 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 boom. So those two look the same. Right? When we do it from a graph, we read it off the graph, and we could be using intervals, interval notation, or inequality notation based on what we see. Now, something to keep in mind, we want to be careful about open circles. We want to be careful about arrows and whether it hits the edge of the graph. But the trickiest of all of them is the from equations. So basically, when I do it domains from equations, I ask myself two main questions. First question, are there any x's in the denominator? No, no. So if it's yes, you want to set the denominator equal to 0. And it's really not equal to 0. And that's because friends don't let friends divide by 0. So, for example, if I had f of x is 1 over x plus 1, I would say, oh, I have an x in the denominator. I make sure I say x plus 1 can't equal 0. X can't equal negative 1. So my domain would either be written like this as inequalities, or we could go in intervals as negative infinity to negative 1, and negative 1 to infinity. So we're basically just excluding that negative 1. Now, let's say the answer to that was no. My second question, is there an even index radical? So that's like even radical. So it could be a square root, could be a fourth root, could be a sixth root, etc. Okay. So if that's a yes, then whatever's under the radical has to be greater than or equal to 0. So that's really called the radicand. The radicand has to be greater than or equal to 0. So an example, square root 3x plus 6. Okay, so if this is my function, I would take this, so if this is my function, I would take just what's under the radical. Notice I left the 4 alone, because I'm not worried about that. I just need what's under the radical, in this case 3x plus 6, to be greater than or equal to 0. And then I solve this inequality. So I can leave it in inequality notation, or I can write it in interval notation, whichever one you prefer. The answer to both of those questions, though, are no. And sometimes you might have a problem that has x's in the denominator and radicals. That's just crazy. Okay, but if the answer to both of those questions are no, then it's all real numbers. Okay, or you can write it negative infinity to infinity. So at the bottom of this page, there are 6 problems. I'm going to do, oh, see, look, that g of x is a little spicy. So what I want you to do is pause the video here and try those 6 problems. Did you try them? Really? Go ahead, pause. It's all right, I'm waiting. All right. So on this first one with f of x, is there any x's in the denominator? No. Do I have any square root even roots? No. So this one is all real numbers. Very easy. I'm going to leave you g of x and this f of x to do on your own. Okay, so this one and this one you do on your own for those two. All right, so then I'm going to do this bottom row because they're a little spicier. So this f of x, I do have x's in the denominator. Do you see those x's in the denominator down here? So I'm going to set that denominator not equal to 0. Now, depending on what it is, because I have a quadratic here, I might factor it or do some other ways. I'm going to go for factoring. X minus 2, x plus 2, and x can't be 2 or negative 2. So this one had 2 values it couldn't be. Again, you can leave your answer in this inequality notation, but you could also write it like this. This is a little much on this one. Alright, and then this g of x, ooh, whoa, 2 things going on. I actually have a radical and x's in the denominator. Do we see both of those things going on? Alright, so I got 2 things I need to write about this one. I need to say x can't be 3 because I want to make sure that I'm not dividing by 0. But then I also have this radicand of x minus 4 has to be greater than or equal to 0. So I have x is greater than or equal to 4, and also x can't be 3. Well, 3 is not greater than or equal to 4, so this is my final answer. It's kind of like if I was drawing a number line saying, we're here and then going this way, but make sure that we don't have 3. Well, alright, we don't have 3. Good. Now, if it had been like a 5 there, then I might have a hole, I'd have a hole over on this side, and I'd be a little more complicated. Alright. And last but not least, h of x is the absolute value of x plus 5. Now, this one has no x's in the denominator and no radicals. So this one isn't all real numbers. An absolute value. There's no value that I will give me a problem to plug in. So, or you can write it this way. And that concludes our fun with functions. So, as a reminder, the ones that you want to upload, f and g right here on page 6. And I want a picture of all 3 problems on page 5. 1, 2, 3, 4, 5. So there are 5 problems you should be sending me. Okay. Have a lovely day.